Welcome to a special version of Raspberry on a Boat. Today we will talk about the Votronic solar charger and how to read out the UART communication of it. So let's start. Yeah, and today we are really on a boat with our Raspberry and we will take a look at our solar module, or rather on our solar regulator charger. This is a Votronic German manufacturer, and this Votronic and all Votronics offer an output to connect a Votronic solar display, which I can recommend, which is nice. However, they were so kind to hand over their protocol to me, a serial protocol, and we want to connect this to our Raspberry. So instead of using the display, we will connect a cable directly to our UART inputs on our Raspberry, getting the data to Node RED, creating a dashboard with charging current, voltage of the battery, voltage of the module itself, and the current status of charging. Votronic offers several chargers or regulators, MPP based ones and normal ones, and they also have a marine version additionally, which has protected electronics against humidity, so which is ideal for using it on a boat, of course. The usually difference is on the watt, how many modules you can connect, of course, but for us the main importance is that all have this solar output. And this output has a special plug. Well, it's not that special, it's quite common. It is common because all telephones use it. So telephones use the RJ12, and this is a two-pole connector. However, they need the RJ12 because you need all 6 poles, all 6 connectors here. And this is because they use pin 1 and 6, which you need to connect. And I bought this adapter. I will put an Amazon link in the description where you can easily grab pin 1 and 6. This is a RJ12, so ideal. However, it was difficult to get it to the Votronic, so I used this extension cable, and this was perfect. I will also link this one. And then you can connect it directly with your Raspberry. However, as I use the daisy head, it's a bit tricky because the daisy head didn't offer the second, third, fourth, fifth UART, which a Raspberry Pi 4 has, as an output. Only the first UART, which is used by the daisy itself. So we need to solder one wire on one receive pin of another UART. That's the only chance. Or you put another PCP to grab the GPIO header completely. So what you need to do is first, it depends now what kind of Raspberry you use. This is now on a 0. Here we want to use the first UART, and then you need to disable here the console, and you need to enable the serial port. And when you do this, you can use pin GPIO pin 14 and 15 for UART, for the first UART. Usually there's the mini UART. Now we did enable the main, the real UART. But, and that's important, if you use the daisy head, this UART is occupied. Luckily, the Raspberry 4 has 5 UARTs. So our first one here on 1450, which is used by daisy head, but we have also 4 additional ones which we need to enable. So I used the one on GPIO pin 5, so that's the input, the receive pin. We just need the receive pin later on of UART 3, and that's what we are going to do now. So you need to edit the config txt, which you find in the boot directory, and we need to set a overlay tree option. So device tree overlay. You see already here, this is UART is enabled, so the full UART, mini UART is off, and Bluetooth must be disabled to get the first UART because it's using the same. And we will now enable UART 3, and that's the only thing you have to do. Put this in, save, and reboot. But I'm on a 0 here today for demonstration, so I can't do that. I will use now pin 14 and 15. And you can see this if you put a list on the device directory and take a look for the hardware connected, and you will see the TTYAMA0. That's the first UART. If you enable a second, or even if you put the fifth UART here on active, it will be called TTYAMA1. So that would be the second UART which you enable. Well, long story, but now let's start up Node-RED and install 2 additional nodes. First of all, an LED node for our dashboard, so the UI LED. This helps us for the bit field to visualize true and false elements. And of course we need for the UART communication a serial port node. This one was the one I found, and it's working fine. And to check if everything is working before you connect the Votronic, you can just simply shorten pin 14 and 15 if you use UART 1, or the other 2 pins, receive and transmit pin of the UART you are using. And that helps to check if everything is working. And for that we simply place the serial in, so that's our new node here, and an output. So that means the upper one is now the output, so we want to send something to the output and it will be received on the input side. And when we want to send something, we can just use a simple inject node, but we need to configure the UART. So, and now we need the TTY device. So I use a 0 here, as I said, so I use AMA0. You can use AMA1 if you have a second UART enabled. This is what I did on my boat. Baud rate is 1000. That's already the one the Votronic is using. And then you need to set how you want to receive a string and how to send it. We will start with receiving a string which has a line feed, and we will send a line feed at the end just to see if everything is working. Let's call this one output because we are sending data here, and the other one is the input node, so we receive data here. That's our RX pin. And when we take a look at the debug node, we see that there's a little error because I forgot, so it's a mistake in spelling. There is an A missing. Now you can just change either of one because they're both the same. So if I add an A here, it's working on the output as well because it's using this as a kind of a variable. So when we send this one, you will see that the timestamp is received, so that works. But Votronic did send an example for their 16 bytes, which they sent. And it starts always with an AA sync byte, so we can use this to sync, and then we receive 15 further bytes, and the last one is a checksum byte. And with these bytes, there's the voltage for the battery, so for our own battery, the voltage of the module itself, and of course the current of the charging current. And there's also a bit register, bit field for the battery status. And there you can see, if the regulator is currently in which mode it is. So if it's in a U1 mode or an I mode and so on. So which phase. We can now change, for simulation of this demo, we can change the inject node to a buffer. And there you can only enter decimal values. I start with 170, which is AA in hex, and another one just as an example. So we switch on the output side to binary buffer, and we will not add the line feed anymore because now we will use the sync byte, so which is AA or 170 in decimal. But this one will only accept hex values. This is also a hint here below. So 170 will not work. We need to enter OXAA. So that's the first sync byte. And then we also need to change how it is split. We will take a fixed length, and the fixed lengths are usually 16 characters later on, but for our demo now just 2. So 2 characters are 2 bytes. And 2 bytes is what we did enter. So 170, which is AA, and 50, which is hexadecimal 50, which is 80 in decimal. So this is working, and now we can change this to 16 and enter all the examples from the Votronic protocol. I just have to convert them to decimal because the example is showing hex. But let's do this now, and now we have all the 16 examples in. The last one is, as I said, the checksum. And let's give it a try. So 211 is the checksum. And we see that now, of course, all 16 bytes are received. What we can do now is, for example, the first thing we should do maybe is to calculate the checksum on our own to see if the transmission was correct, which helps to identify if there are some transmissions which are broken. So you should check if the checksum is okay, and if not, throw away the whole message. It's sending messages anyway each second or something, so no worries if one message is gone. So let's take a function node here, and in this function node we will just define a variable which we call check. We start this with 0, and we can put a semicolon, but it's not necessary here, Node-RED on JavaScript. So I will just leave that. We do this in a loop because otherwise we need to have a lot of OR conjunctions, because this is how the checksum is built. So we start with 1 because the sync byte is not included in the checksum, and we also skip the last one because this is the checksum. So we go from 1 to 14. And what we do here now, you can see on the top, that's how the checksum is calculated, 14 to 1. That's exactly what we did. And it's an OR conjunction between the elements. So we did this now, and of course we can create a new object for payload because we want to put a lot of items later on in here. And this is the first one, which we call checksum with a variable. And let's give it a try. You remember 211 was the one which was given in the example here. And you see our calculation also shows 211. So we have the checksum ready here. Okay, so this was our first task. Second task is, of course, to calculate voltage, current, and so on. So the content of our payload. The first thing what we can do is take the ID. This was the first byte, so after the sync byte, and hand this also over to our output object. But in the ID there's nothing which we can use later on. But just for information, maybe it's nice. But now it's getting more interesting. We want to put out the voltage of our battery, which is an unsigned integer 16. 16 means we need 2 bytes, and you always need to know which is the LSB and the MSB, so the least and most significant bit, or byte in this case. Also the complete byte is so the number 3 is the MSB and number 2 is the LSB for the voltage of the battery. And that means we need to shift byte number 3, so to the left side, 8 positions to the left side, which adds 8 zeros at the end. And then we can add the LSB, which is now number 2. And with this we get our voltage of our battery. In this example, I think it was 14.4 volts. Let's see what comes out. And you will see there is 1440, and you need to know that 1 bit represents 10 millivolts. So we have to multiply this value by 10 to get the millivolt value and divide it afterwards by 1000 to get the volt value. So let's do this. We multiply this by 10, Now we have the millivolt value, which is obviously correct now, 14,400. And if we divide this by 1000, we get our 14.4 volts, which fits to a board battery. By the way, this is not a misspelling, this is the German board. If you write it in German, it's the A is missing, so it's BORD. Yeah, so that's exactly the calculation, but there is a second way, which is a little bit easier, especially for the signed ones, and that is using a method which is called read, and then U for unsigned int 16, because it's a 16-bit integer. And then you need to tell them the first byte, which is number 2. And now you can define either LE when the number 2 is the least one, or a BE if it's the most significant bit. So in our case, it's LE. And with that, we also get the same result, so no difference. But it's an easier calculation, especially for signed, because there you don't have to do it on your own to see if it's bigger than half of the complete value. And for the solar current, so the charging current, which is, I think, the most interesting thing, we need a signed 16-bit integer. Now we use this method again, but there's a little deviation because we just skip the U. We take read int 16, which is exactly the signed 16-bit integer, and because it's the same method here, it's LE. We will tell them number 6 is the first one, LE, but this is the lower byte, little endian, and number 7 is the other one. So that's how this is. BE would be big endian, but then 6 would be the bigger one and 7 the little one. It's given in milliamps when you multiply this by 10, but I divide it directly by 1000 to get it in amps, because also here it's 10 milliamps per bit. And we hand over the variable to our object, and we get 1.2 amps as a result. So that is what Votronic did put in their example, which makes sense. Okay, and we have a last thing to do. We need to interpret also bit fields. So bit fields mean there are 2 bit fields existing, where each bit stands for something. In this first bit field, it is the charging phase, so as it's currently E, U1, U2, U3. And in the other bit field, there could be also the combination that bit 1 is set and bit 3 and so on. In this case, usually just 1 bit should be set, and we can check this. We will check each bit individually, so if 2 are set at the same time, we can also visualize this. And for that, it's shifting a 1 to the left by the number of bits where you want to check. So in this case, we don't need to shift it at all, but I just do it this way to see if this, what we do there. And then it's an AND to check if the 1 is at this position. So we check if our byte at position number 13 has a 1 on the first, so position 0. And in this case, we say I phase is true. And we can do exactly the same for bit number 1, or so that's bit number 1 now, position number 2, let's say. That would be U1 phase, and so on, U2, U3, and we do them all together, of course, so we can visualize later on in which phase the current charging process is. I did this already, I did prepare this, so when you take a look here, I will check each bit 0, 1, 2, and 3, and also there's status for the charger itself, and also their same method, and we put this later on to the dashboard. And we have also another voltage which we didn't realize so far, but you can find my example on GitHub, also with my object with all the input, so you can use this to not start from the scratch. And also the visualization can be found there, because it doesn't make sense now to go into the dashboard things. I think we did this in several other tutorials. Take a look at my example. As I said, what I do here is putting the object content which we have below to the different dashboard elements, so a gauge, or also to the LEDs which we downloaded to see what is false and what is true. So we can take a look at the dashboard itself. What I did so far is, on the left side you see the charging current and the battery and voltage of the solar panel, which is, according to the protocol, only available for the MPP series, and then the charging phase and the status of the charger itself. And on real values this is working. There was no sun on this one here, because then you see that both voltages are the same, but we see that it's working, and you can apply this on your Raspberry. As said, you can find this on GitHub, so enjoy this and use it, and bye bye.